So in we will study linked representation of the queue. We will see how insertion and deletion operations can be performed using linked representation of the queue. And then we will study another variation of queue, which is called DEQ, double-ended queue, in which insertion and deletion operations can be performed at both ends. Okay. So first, let's discuss the linked representation of the queue. So in the previous lecture, we discussed the array representation. In the array representation, uh, we use a circular array. Okay, the circular array, after the last index, we go to the first index, right? So a circular array is used to implement the queue in the array representation of the queue. In the linked representation of the queue, a linked list is used. So a linked queue is a queue implemented as a linked list with two pointers. First pointer front, second pointer rear. One pointer points to the nodes which is in the front end of the queue, and rear pointer points to the rear end of the queue. Remember that the items can be deleted only from the front end, right? And can be inserted only at the rear end. Okay. So we have two pointers, front and rear pointer. Front pointer points to the front end from where items can be deleted, and rear pointer points to the rear end of the queue where new elements can be inserted. Okay, so this is an example of how linked lists are used to represent the queue. So there are three elements in the queue, double A, double B, and double C, and this is the front end of the queue, and this is the rear end of the queue. Okay, so we have a front pointer. This is the front pointer, which points to the front end. That is the first element at the front side. Okay, and we have this right pointer, which is the rear pointer, which points to the rear end. That is the first pointer at the rear side of it. Okay, so insertion in a queue. Now you have to insert this new element double D into this queue. So insertion can take place only at the rear end. Okay, so here after double C we will insert double D. So what we'll do? Okay, first we will create a new node. Okay, name it as new. Then we copy the value of the new element double D in the information part of the new node, right? And then we have to modify some pointers. Okay, what we'll do? Now this new node will become the first node in the at the rear side. Okay, so this pointer, okay, that is the pointer in the last node at pointer at the first node at the rear side will now point to this new node, right? Okay, and the pointer in the new node points to null, right? And the rear pointer will point to this new node, like this. Okay, so in fact this is not a null value. Okay, this is a pointer which points to the new node, and in the pointer part of the new node points to null. Okay, and the rear pointer points to the new. So three pointers needs to be exchanged, needs to be adjusted. Okay, so that is this pointer. Okay, this pointer will point to the new node. Okay, and the pointer in the new node points to null, and the rear pointer points to the new, right? So this is the steps in the insertion in a queue using linked representation. Now, how to delete from a queue using linked representation? Okay, deletion can take place only at the front end. Okay, so it means that you can delete this node also. Okay, so what is the process? The process is very simple. You delete this node, so the front will now point to the next node from the front side. Okay, only one adjustment is required. That's all. The front points to the next node, double. So this is the deletion operation. So it's comparatively simpler than the insertion operation because one operation is required. The front points to the next. Okay, so what are the advantages of the linked representation of the queue over array representation of the queue? The first advantage is there is no need to check for the overflow condition because you can always add a new node. Okay, in the circular array representation, is the size of the array is fixed. If the array is full, then you cannot add a new node. Okay, there will be overflow condition if you try to insert a new node and that circular array is full. Okay, but in case of linked queue, there is no need to check for the overflow condition because you can always add a new node. Okay, and in this book, in fact, in the book of book by the Lipschutz, we are also maintaining a wait list. Usually the avail list, that is usually the set of all the free nodes are handled by the operating system. Okay, the space for the new nodes comes from the heap section, and this is managed by the operating system. But in this course, we are assuming that this garbage collection management is being managed by the user himself. Okay, and the collection of the set of all the free nodes is maintained as a linked list called avail. Okay, so if you are maintaining your own avail list, then you need to check for the overflow condition. Otherwise, there is no need to check for the overflow condition if you are using a linked queue, right? So this is the first advantage. You can always add a new node, and there is no need to view the queue as a circular queue for efficient management of a space. Right? This is the second advantage. Okay, in the array implementation, we assume that after the nth index, we go to the first index. We treat the array as a circular array, right? But in the linked list implementation, there is no need to assume such thing. So this is the second advantage. The things are comparatively simpler here. Okay, so now the algorithm for the insertion. This is the insertion algorithm assuming that the garbage collection is done by the operating system, that is not done manually by the user, right? So it is in the algorithm, we don't consider the avail list. So what we'll do, we create a new node, and the information part of the new node, we store the new element value item, okay, and then in the link part, we store null, okay. Then we check if the list is already empty or not. Okay, if the list is empty, that is if the front is null, okay, it means that this new node will be the first node. Okay, and in that case, we will store front is equal to rear is equal to null, right? Else we will store rear link is equal to new, right? Because the new node will be inserted at the rear end. So now the rear of the link, in the link part of the current first node at the rear side, okay, we will store the pointer to the new node, okay, and now the rear pointer will point to the new node. That's all. So this is the insertion algorithm. Okay, this is the insertion algorithm when you consider the avail list. right? So if you consider the avail list, then you must consider for the overflow condition, right? So check if some space is available in the avail list. If avail is equal to null, then write overflow and exit, right? And if there are some new nodes in the avail list, then what you will do, you will remove the first node from the avail list. So set new is equal to avail and avail is equal to avail. Okay, that is you remove the first node from the avail list. Okay, and the pointer to the first node is new. Then store the value of the item in the information part of the new node. Okay, and its link value is set to null, right? Then in the fourth step, you check if the queue is empty. The condition for that is if front is equal to null. Okay, if queue is already empty, then this new node will be the first node, and in that case both front and rear pointer will be equal to new. Okay, the only node. Okay, else, that is if there are some nodes in the queue already, in that case you will modify the rear pointer. Okay, that is the first node at rear side will point to its new node, and the rear pointer will point to the new, right? So this is the insertion algorithm when the avail list is also considered. Now the deletion algorithm, deletion is comparatively simpler. Okay, so simply check for the underflow. If the list is empty, then obviously you cannot delete. So underflow and exit. And if there are some element, then simply set front is equal to front link. It is a front pointer will points to the next node. Okay, so the first node at the front side is deleted, and this completes the deletion algorithm. This is the algorithm when avail list is considered. Okay, so check if uh, there is a node or not. So if front is equal to null, it means that there is no node in the list. So underflow and exit, right? Then delete the node and collect the value in a temporary variable temp. So temp is equal to front, okay, and collect the value in the item variable, right? And then you simply uh, points you set the front pointer to the link tab. Okay, that is front is equal to link tab means now front points to the next node. Okay, and that deleted node will be added to the avail list. So link temp is equal to avail and avail is equal to temp. Okay, so this deleted node is added as the first node in the avail list. Then okay, so these are the methods, these are the algorithms that how insertion and deletion are performed in the queue when it is implemented as a linked list. Now, deck. Deck is also a queue data structure with some variation. Okay, so deck is basically a double-ended queue. So D is for double, E is for ended, and this queue, QUE is for queue. So double-ended queue. So what does it mean by double-ended queue? In the double-ended queue, insertion and deletion can be performed at both ends. In the normal queue, insertion can be performed only at one end, which is called the front end, which is called the rear end, and deletion can be performed only at the other end, which is called the front end, right? In the double-ended queue deck, insertions and deletion can be performed at both ends, okay? And in the deck, ends are called left and right end, right? Because insertions can be performed at any end, likewise deletion can be performed at any end. So there is no need to call them like front and rear. We call them left and right. Okay, an insertion and deletion can be performed at the left end and also at the right end. Okay, so deck is a linear list in which elements can be added or removed at either end but not in the middle. Okay. So insertion and deletion can be performed at both ends but not in the middle. And deck is implemented by a circular array deck with pointers left and right, which points to the two end of the deck. Okay. So in fact, deck can be implemented using array or circular array, and they can also be implemented using linked list. Okay. So like Q can be implemented using circular array or linked list. Likewise, deck can also be implemented using a circular array or a linked list. Okay. So the deck we have two pointers, left and right. Okay. So example of a deck, for example, consider this deck. In this scenario, we are using a circular array to represent a deck. Okay, and in the current state of this deck, we have four elements: double A, double B, double C, double D. Okay, the left pointer is 4. Okay, and the right pointer is 7. Okay, the size of the circular array is 8. So it means we can store at most 8 elements. Currently, there are 4 elements. The left pointer is 4 and the right pointer is 7. Okay, so insertion can be performed at both ends, right? Now another deck. Okay, here uh, circular array size is 8. The left pointer is 7. This is the left pointer and the right pointer is 2. Okay. We are assuming that this is array is a circular array, that is after the last index 8 we go to the first index 1. Okay, variation of deck. There are two types of deck. First, input restricted queue or input restricted deck. So input restricted deck is a deck which allows insertion at only one end of the list but allows deletion at both ends of the list. Okay. So input is restricted only at one end, but deletion is allowed at both ends. Okay, second type of the deck is output restricted deck. So output restricted deck is a deck which allows deletion only at one end but allows insertion at both ends of the list. So in the output restricted deck, output is restricted to only one end and the insertion is allowed at both the ends of the list. Okay, so we have two types of deck: input restricted deck and output restricted deck. Okay, now examples of insertion and deletion in a deck. So say this is the current state of a deck. The left pointer is 2 and the right pointer is 4. We have 3 elements and the size of circular array is 6. Now we insert F to the right. Okay. So here to insert an element, we need the value of the new element. Okay, and we must also specify the end, left or right, where the new element is to be inserted. Okay, and this is the additional information we require in the deck. In the normal queue, we require only the value of the element which is to be inserted, and that new element will always be inserted only at the rear end, right? But here in deck, the element can be inserted at either end, so we must specify where at which end this new element will be inserted. Okay, so we say that we have to insert new element F at the right end. Okay, so the right pointer is 4, Okay, so new element f will be inserted here, right? So f will be inserted at the next free location at the right side. Okay, and the right pointer will be incremented by 1. So this is the insertion in the deck. Okay, now deletion, example of deletion in the deck. So left is 2, right is 5. Okay, the 2 letters on right side is deleted. So at the right side, F is, so first F will be deleted, right becomes 4, then the second letter D will be deleted, right is decremented, so right becomes 3. Okay, now in example of insertion, so this is the current position, current state of the deck. Okay, left is 2, right is 3. Okay, now insert 3 new elements K, L, M, N at the left end. Okay, so first insert K, then insert L, then insert N. Okay, so left hand is 2. So at the left of the left pointer we have 1, index 1. So we will store first element K at location 1, right? Then insert L, but 1 is the lowest index of this array. So where we will go? Since we are treating this array as a circular array, so after the first location, we will go to the last location. Okay. So next element L will be inserted at index 6, right? Then the next element M will be inserted at index 5. Okay. So in the deck, the array is circular from both sides. Okay, from both sides means if you reach to the last location, okay, and then you insert a new element, you will go to the first element. Likewise, if you are inserting new elements at the left side and you reach the lowest index, then from the lowest index you will go to the last index. Okay, so in the deck you consider the array as circular array from both sides. After the last index, you go to the first index, and from the if you have reached to the first index, you go to the last index. Okay. In the normal queue implementation, okay, you consider the array as circular array only in one direction. That is, from the last location, you go to the first location. There is no need to consider the array as circular array from the other direction. That is, there is no need to go from the lowest index to the other index, the highest index, because at that side, that is at the front side, only deletions are allowed, insertions are not allowed. Okay, so that is not required in the implementation of the normal queue. Okay, now application of deck, application of double-ended queue. So several applications are can be identified. Okay, one simple application is palindrome checker. Okay, palindrome means palindrome is a string. Palindrome is a string which is same from both the sides. Okay, that is, if you spell this string radar, RADAR, from left to right, okay, or right to left, the spelling is same, RADAR from left to right, and also from right to left it is RADAR. Okay, so this is palindrome. Okay, so using a deck you can check whether a string is a palindrome or not. Okay, and the algorithm is very simple. Okay, so first you insert this string radar in a deck. Okay, so you add to, say, this is your left hand and this is your right hand, right? So you add the letters of the string from the left side one by one. Okay, so RADAR will be inserted. Once the whole string has been inserted, okay, what you will do, you delete a letter from the left side and you also delete a letter from the right side. Okay, if the deleted letters from both sides are same, then you go on to delete more letters from both left and right side. Okay, and then compare if they are same. Okay, then you go on to compare more letters after deleting letter from both left and right side. Okay, and comparing them, and this will continue until the left index and the right index becomes same, and all the deleted letters are same, then it means that the string is a palindrome. Okay, if any letter is not same, it means the string is not a palindrome. Okay, so for example, in this step, in the first step, you have inserted this string radar into the queue into the deck. Okay, and then in the second step, you delete a letter from the left side, that is R. Then you delete a letter from the right side, compare them, they are same, RR. Then you go on to delete the next letter from both sides, AA, same. Okay, then delete the next letters, so it is same, D, and left pointer or left index becomes same as the right pointer. Okay, so it means that this string radar is a palindrome. This is a simple application of the deck. Another application in the job scheduling algorithm. Okay, is still job scheduling algorithm. So what is job scheduling algorithm? Job scheduling or process scheduling algorithm. In fact, you will study the job scheduling and process scheduling algorithms in great detail in the course of operating system. Okay, so what is process scheduling? Okay, we have various programs. Okay, and when you execute programs, that program becomes a process. Okay, so process is an active entity. So a process requires some resources like memory, and it has a program identifier, and it has several resources associated with it. A process also requires CPU time. Okay, and usually there is a single CPU. Okay, and several processes can be executed at the same time. Okay, at one time only one process is executed by the CPU and other processes are active but not being executed by the CPU, but they are waiting for the CPU. Okay, so if when one process finishes its execution, okay, then the question arises that which process will be executed next by the CPU, because there might be several processes waiting for the CPU. Okay, so we must schedule the processes. We must schedule them. That is, we must decide which process will be executed by the CPU next. So this task is known as scheduling algorithm. Okay, job scheduling algorithm or the process scheduling algorithm. So there are several scheduling algorithms. The simplest one is FIFO scheduling algorithm, first in, first out. That is the process which is submitted first is executed first. Okay, so first in, first out. The process which is submitted first is executed first. Okay, and obviously you know that FIFO means queue data structure. Okay, so to implement the first in, first out scheduling algorithm, queue data structure is used. Okay, and there is another scheduling algorithm which is called A-Steal job scheduling algorithm. And to implement the A-Steal job scheduling algorithm, we use deck. Okay, because in the FIFO, okay, in the FIFO scheduling algorithm, okay, in the FIFO scheduling algorithm, the processes are inserted only at one end and deleted from the other end. Okay, that is when the process is submitted, it is inserted at the rear end, and when the process is and when the CPU becomes free and CPU requires some process for execution, the process which is at the front end of the queue is deleted and allocated to the CPU, right? So this is FIFO scheduling algorithm. In the A steel job scheduling algorithm, the process can be inserted only at one end but deleted at both ends. Okay, so A steel job scheduling algorithm requires input restricted deck. Insertion takes place only at one end, but deletion can be done at both ends. Okay. So what is A steel job scheduling algorithm? A steel job scheduling algorithm is used on multiprocessor system. Multiprocessor system means there are multiple processors. Okay. Multiple systems. Any system has its own processor, or there is a single large system which has multiple processors. So each processor had its own cache, has its own main memory control unit, right? So So in multiprocessor system, we have multiple CPUs and each CPU maintains its own queue, its own deck, double-ended queue, right? So when a process arrives on on a processor of a multiprocessor system, that process is added at the rear end of the queue of that processor, right? And when processor needs some process for execution, the process which is at the front end of that deck is deleted, okay, and allocated to the CPU, right? So I'm using front and left end as same. Likewise, rear and right end as same. Okay. So I repeat, when when a processor requires some process for execution, the process which is at the front end or at the left end is deleted from the deck and allocated to the CPU. And when a new process is submitted, it is added at the rear end. Okay, this is the normal process. Now, what happens in the multiprocessor systems? We must perform load balancing. So what is load balancing? Okay, that is the load on all the processors must be same. It must not happen that one processor is sitting idle and several processors are waiting for the second processor, right? So all the processors must be kept busy. So when a processor to balance the load on all the processor, when a processor becomes free, so it can fetch a program, it can fetch a process from some other busy processor. Okay. So how it fetches a process from a busy processor? Okay. So here the deck is used. So in this scenario, okay, a free processor fetches a process from busy processor, okay, that is it borrows or it takes a process, that is free processor takes a process from busy processor, okay, and which process is taken by the free processor? The process which is at the front side, okay. So a busy processor, when a busy processor becomes free, it takes a process from its own deck, and that process which is at the rear end is taken by the busy processor, right? But when a free processor takes or borrows a process from a busy processor, it takes that process which is at the front end, okay. So in this case, the process which is at the front end is deleted and given to the front processor, okay. So it means that the deletion can take place at both the ends, okay. When busy processor requires a new process for execution, the process which is at the rear end is deleted and given to the busy processor. And when a free processor borrows a process from the busy processor, the process which is at the front end is deleted and given to the free processor. Okay. So in this scenario, the deletion can take place at both the end, front and the rear. Okay, but the insertion takes place only at the rear end. When any process is submitted, it is added at the rear end of the deck. Okay, so a steel job scheduling algorithm uses input restricted deck. Okay, so these are two application scenarios where decks are used. Okay, in the next lecture, we will study another variation of the queue called the priority.